So the first step would be our null hypothesis, laying out those proportions. P1 was 0.4, P2 was 0.25, P3 was supposed to be 0.05, P4 was supposed to be 0.1, and P5 was supposed to be 0.2. Potentially we could use the language H0, the observed frequencies are as given by our null hypothesis up above, but we'll just spell it out. 5 is not too bad. And then the alternative, at least one proportion is different, or you could say 2 or more. And then for step 2, recognizing that whenever you have that single row of observed values and these expected values that we then compute, immediately that's goodness of fit. And therefore we are using the chi-square distribution. Big new thing. And it is going to be right-tailed. And let's see, with 5 categories, the degrees of freedom, 5 take away 1 will be 4. So we could set up a critical value now using the chi-square table. So let's see, our alpha was 0.05 with degrees of freedom 4. So go look up in your table, and the chi-square table gives the critical value of 9.488. So that's this cutoff right here. If our test statistic is greater than that, we are going to reject. All right, so step 3 on the calculator, if you've got that built-in test, you've already got your observed frequencies in L1, you've got your expected frequencies in L2, so either you have the chi-square GOF test, it's got to have that GOF in it, or you're going to then calculate L3, which is L1 minus L2 in parentheses, so you can square it, and then divide by L2, and then run one variable stats on L3, and I should mention that's in the stat calc menu. Right, and either way, then I get a test statistic, chi-square equals 14.393. And if you have the newer calculator, you just get to read off the p-value of 0.0061. If you need to, remember you can use chi-square CDF on that test statistic to get the p-value also. So it's up to you. If it's worth it to get that point, then by all means, please do it, or get it automatically. That's great. So then this now should be fairly familiar. We bring down our diagram. If you didn't do it yet, this would be a good time to do it. We've got our reject zone always in the right tail at that critical value of 9.488. Bring in your test statistic, 14.393. For sure that's in the reject zone. And then the p-value compared to alpha. Again, this is all very familiar, hopefully, from our earlier work. And our p-value is definitely smaller than that significance level. So the first thing we write in our conclusion is that we're going to reject the null. And then we're going to have to figure out what to say for the alternative. So there's no context here. So maybe something like this. Here's one thing you could think about saying. At the 0.05 significance level, evidence does not support the null. And I'm saying it that way because look at the original problem. Test the hypothesis that the distribution is as given by the null. So I'm actually going to say no, it's not like the null, and it appears that at least one proportion is different from those given values. All right, there's your first taste of the goodness of fit test. So number 23. That last example, we were given all those different proportions to work with. Here's an example that says the number of false fire alarms were counted each month at a number of sites. The results are given in the following table. So January through December, 12 months. Here's all the various alarms. And we're going to test the hypothesis that the false alarms are equally likely to occur in any month. Use alpha equal to 0.01. So the first thing we have to do is work out our expected values, and that involves finding the total for all these fire alarms. We got to add those up. I won't give you anything nearly this big on the final exam, but we do have to do this now. And there are 427 entries in this table. So when we go to do our expected values, all right, what's given in the table are the observed values. We're going to take that 427 and divide it by 12. And that's going to be the same exact entry in all of these. And I don't think that goes in evenly, so we want to minimize error. And so we're just going to enter that fraction over and over into the calculator, into L1 and L2. So L1 again will be the observed values, and then the expected values will go into L2. And here we go with our hypothesis test. First step, this is the example where all the proportions are supposed to be equal. So I might write something like the probability or the proportion in January is equal to the proportion in February, and is equal to ... because I don't want to write out all 12. And that's equal to the proportion in December. That's okay to do when they're all equal. And then our alternative is that at least one proportion is different. And I don't mind some abbreviating. One prop is different. All right, we recognize that with that single row of observations and then our expected values, that's a goodness of fit test. So different from anything else we've done so far. And so then we know that that's going to be the chi-square distribution. It's right-tailed. And with 12 months in the year, the degrees of freedom, 12 minus 1, will be 11. So if we want to set up our critical value, we can do that. We've got our 0.01 entirely in that right tail, the chi-square table, with that 0.01 in the right tail and the degrees of freedom 11 gives 24.725. So that's our critical value. Let's say one thing and write another. Oh, it's bad. All right, and then another chance to practice on your calculator. You're going to write yourself notes on, you get 2 index cards for the final, so you want to make sure you write down some good calculator notes. You're going to put the observed in L1 and the expected into L2, and then either run your chi-squared GOF test or do your L3 equals L1 minus L2 all squared over L2, and then add one variable stats on top of that to get the sum on L3. And I get the test statistic, chi-square is 27.792. And the other degrees of freedom here again was 11. And then the p-value, either you get it easily or using chi-square CDF, 0.0035. So yep, if we do our comparison, drawing our quick picture for the reject H0 region, can be quick. Try to make it fairly accurate if you can. I'm being a little scribbly here, as you can see, so try not to get any worse than that. And yep, 27, our test statistic, 27, 28, 27.792 is far out there to the right. And our p-value compared to alpha, 0.0035 compared to 0.01. Yep, we've got a small p-value, so we are indeed going to reject the null. And, oops, sorry, that's our step 5. So we need to make a statement about fire alarms. So this is what I wrote. At the 0.01 significance level, Evidence suggests that at least 1 month has a significantly different number of false alarms than the others. I'm doing a little inspecting up there. Look at February with 15. That looks unusually low. So that was enough probably to throw everything off. Maybe some of the other months as well. And that wraps up 12.1.